If you take a funnel like this and fill it to the top with some water that's been dyed blue and pop the cork out, it's going to take some time to drain, but the question is, how long? Welcome back to Engineered Bets. Today's line is 4.5 seconds, which is about as long as it takes for the Lakers to blow a lead, and it's your job to take the over or the under. And don't worry, we'll talk about adding this guy at the end. So how on earth was the line set? Well, the outlet has a radius of about 0.007 meters, and it was modeled as a cone with an angle of 33.4 degrees, meaning the initial height of the reservoir from this bottommost point was about 0.126 meters. To solve for the time to drain, you need to relate the height of the reservoir, which will be changing, to the time, so you can solve for the time when the reservoir height reaches zero. First, using the conservation of mass, you know that how the mass of water changes with respect to time is going to be equal to the mass leaving at the outlet surface, aka the mass flow rate at the exit. Mass is just density times volume, and the mass flow rate is just density times the exit velocity times the exit area. Since we'll assume water is incompressible, the density is a constant that can be cancelled on both sides. After reminding ourselves that we want the reservoir height related to time, we can see that there are two variables left that we need to relate to height in order to solve this, since the outlet area is a constant and we do want time to be in the equation. To relate the velocity at the exit to the height of the water at all points in time, we can use Bernoulli's equation, which essentially compares the energy per unit volume at two different points in a flow, at the reservoir height and at the bottom of the funnel. The pressure at the surface and the exit are both at atmospheric air pressure, so these terms cancel. And the height of the exit is always zero based on our defined axis, so this term is zero. Lastly, it was assumed that the water at the surface has a negligibly small velocity because its cross-sectional area is much larger than that of the exit, so even if the water is shooting out somewhat fast at the bottom, the reservoir height would go down much slower. This could be a potentially costly assumption once the water starts to drain and the reservoir area does approach the exit area, but that will be something for you to factor into your prediction. Anyway, now we can just use algebra to solve for the exit velocity and plug this back into the conservation of mass. Now there's only one variable left that we need to relate to height at all points in time, which is the volume. And for that, we can just use the geometry of the funnel. If instead of a funnel it was just a cylinder, an infinitely small change in volume would be equivalent to an infinitely small change in height times the cross-sectional area, which is just pi r squared, where the radius is a constant. Unfortunately, for a funnel, the radius is not a constant, but rather a function of height. Luckily, we do know exactly how the radius changes with the reservoir height from measuring the angle of the funnel. So the slope of this line is just rise over run or tangent of that measured angle. After plugging this function in, we've now related the volume to the height, so we can plug this equation back into the conservation of mass, and we've got our final differential equation where the only non-constants are height and time, which was the ultimate goal. To solve this, we need to separate the h and t terms and integrate. I'll plug in all the constants now to hopefully make things look less overwhelming. For the height, we'll integrate from the initial height of the reservoir to 0 when the funnel is empty, and for the time, we'll integrate from start time 0 to the final drain time, which we're solving for. After integrating, we now have an equation that estimates how long it would take to drain for any initial height we wanted, which is pretty cool. Plugging in the initial height for our example where the funnel is filled to the top, and you get that the funnel should drain in about 4.5 seconds, and that's how the line was set. Pause now to predict how reality will vary from this model. And now it's time to see what actually happened. As you can see, the funnel actually took 6.09 seconds to drain, meaning the over has hit. Congrats to those who picked correctly. If I added a long tube and did it again, still only looking at the time for the funnel to be empty, you might be surprised to find that it takes significantly less time. Why do you think this is? Let me know in the comments, and as a hint, watch it again while listening closely. I'd like to give a huge thanks to the sponsor of today's video, SaneSmart, for sending me the 3D printer that I used to mount the funnel to the wall. I'm by no means an expert in 3D printing, but I was incredibly impressed with how easy it was to get started with this Creality K1C 3D printer, and it took me less than an hour after opening the box to get my first test print going. SaneSmart also sells other cool products like 3D scanners, CNC machines, and laser engravers. If you want to check out any of these and more, you can use the link in the description to help support the show. Thanks for watching to the end, and I'll see you next time.